In the far reaches of our solar system, beyond the orbit of Neptune, something unusual is happening. A mysterious force is pushing around icy objects, and clusters of these objects have unusual orbits that can't be explained by the known planets alone. Scientists think this could be caused by a massive hidden planet, often called Planet 9. First suggested in 2016, this potential new planet has fascinated astronomers. Interestingly, this isn't the first time a planet has been proposed using mathematics. Neptune and Pluto were both discovered because their gravitational influences were predicted before they were seen through a telescope. Astronomers detected irregularities in Uranus's orbit and later in the Kuiper Belt objects, leading to the discovery of these distant celestial bodies. A century later, we're in a similar position with Planet 9, continuing the fascinating tradition of using mathematical predictions to reveal hidden planets. Some scientists speculate it might be a rogue planet captured by the sun's gravity, while others suggest it could have formed from the same gas and dust disk as the other planets. If Planet 9 exists, it is estimated to be 10 times more massive than Earth, and to orbit the Sun at a distance of 400 to 800 astronomical units, which is 400 to 800 times the Earth-Sun distance. Astronomers have been diligently searching for clues, utilizing powerful telescopes and sophisticated computer models to track its effects. After years of sky watching, solving mathematical puzzles, and conducting complex simulations, they now possess the strongest evidence yet for Planet 9's existence. This discovery adds an exciting twist to the story of hidden planets. So, what evidence have researchers uncovered in their search for Planet 9? Despite our ability to discover exoplanets located hundreds of trillions of miles away, why has it been so challenging to directly detect Planet 9 within our own cosmic neighborhood, even with some of the most powerful telescopes available? Finally, and most intriguingly, if Planet 9 does exist, how did it end up so far on the outskirts of the solar system? Before we dive into these questions, make sure to subscribe to our channel for regular space updates. Although Planet 9 was first proposed in 2016, its story really began soon after Uranus was discovered in 1781. Over time, astronomers noticed something peculiar. Uranus wasn't moving exactly as their calculations had predicted. It seemed to accelerate and decelerate in its orbit, suggesting an unseen force might be influencing it. In the 1840s, mathematicians Urbain Le Verrier in France and John Couch Adams in England independently theorized that Uranus's irregular movements could be due to the gravitational pull of an unseen planet. Using complex mathematics, they predicted the location of this invisible planet. This bold hypothesis relied solely on mathematical calculations to propose the existence of an unknown world. Le Verrier sent his predictions to Johann Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant aimed their telescope at the part of the sky Le Verrier had indicated. To their astonishment, they discovered Neptune on their first night of searching, very close to the predicted location. This was a remarkable achievement, marking the first time a planet had been discovered through mathematical prediction rather than by chance observation. After the successful discovery of Neptune in 1846, astronomers initially believed they had completed the major planetary map of our solar system. However, tracking Neptune's orbit revealed subtle but persistent deviations from its predicted path, much like those observed with Uranus. Given the previous success of predicting Neptune's existence through gravitational influences on Uranus, astronomers wondered if this method could unveil yet another distant planet. This led to the discovery of Pluto after more than 8 decades. On February 18, 1930, Clyde Tombaugh, a young astronomer at the Lowell Observatory, identified a faint, distant object moving against the backdrop of stars, confirming a new celestial body. Initially hailed as the long-sought Planet X, Pluto was later found to be much smaller than anticipated. Pluto's mass was insufficient to explain the gravitational anomalies in the orbits of Uranus and Neptune, indicating the presence of another undiscovered object beyond Neptune's orbit. In 1951, Dutch-American astronomer Gerard Kuiper predicted that there could be several icy objects beyond Neptune, with Pluto being part of a larger collection known as the Kuiper Belt. The first direct observational evidence of Kuiper Belt objects, KBOs, came in 1992 when astronomers David Jewett and Jane Liu discovered 1992 QB1, a small icy body beyond Neptune. This discovery confirmed a population of objects in the region Kuiper had predicted. The identification of hundreds more KBOs followed in the 1990s and 2000s, solidifying the Kuiper Belt as a significant part of our solar system. As more objects were found beyond Neptune, the term trans-Neptunian objects, TNOs, was introduced to encompass all objects orbiting the Sun beyond Neptune. TNOs include any small body in the solar system orbiting the Sun at a greater average distance than Neptune, which is about 30 astronomical units, AU. An AU is the average distance between the Earth and the Sun, approximately 150 million kilometers or 93 million miles. As the catalog of known KBOs expanded, the idea of a single massive Planet X fell out of favor. Astronomers began to believe that the cumulative gravitational effects of these many smaller bodies could explain Neptune's orbital irregularities. However, in 2003, an intriguing discovery shifted the focus back to the possibility of a large, undiscovered planet. Planet 9's orbit is likely highly elliptical. This means that it could spend most of its time in the most distant and darkest regions of its orbit, far from the Sun's illumination. When it is at these farthest points, the planet would be even fainter and harder to spot. The vast area of the sky where Planet 9 could be located. This wide search area requires astronomers to meticulously scan large regions, often rechecking and verifying observations to ensure nothing is missed. Finally, the planet's slow movement across the sky complicates detection efforts. Because of its immense distance from the Sun, Planet 9 moves very slowly relative to the background stars. This slow movement means distinguishing it from the background stars requires prolonged and repeated observations. Astronomers must carefully track potential candidates to confirm they are moving objects, not just stationary stars. Given these challenges, simulations become an indispensable tool in the search for Planet 9. Simulations enable researchers to model complex systems and predict behaviors that are difficult or impossible to observe directly. Let's have a look at how researchers used simulations to find the strongest statistical evidence of Planet 9. The orbits of TNOs are not stable over long periods. Over millions of years, Neptune's strong gravitational pull can alter their paths, scattering them widely or even ejecting them completely from the solar system. This dynamic indicates that TNOs are continuously pushed into orbits intersecting with Neptune. To investigate this further, a research team set up simulations based on the initial conditions presumed for the formation of the inner Oort cloud. The Oort cloud is thought to be a distant, spherical shell of icy bodies encircling the solar system, extending from about 2,000 to 100,000 astronomical units from the Sun. They chose TNOs with perihelia greater than 30 AU and semi-major axes ranging from 100 to 5,000 AU, resulting in a simulation of 2,000 total particles. The research team ran two sets of simulations, one including the hypothesized Planet 9 in its predicted location and another without Planet 9. The results indicated that Planet 9 could affect the orbits of certain TNOs through the direct coupling of the Runge lens vector. This vector describes the shape and orientation of an orbit under the influence of a force like gravity. Its direction gives the orientation of the ellipse, and its magnitude is directly related to the orbital eccentricity. A zero-Runge lens vector corresponds to a circular orbit, while non-zero values indicate elliptical orbits. Planet 9 can make these orbits more stretched and change their inclination angle. The simulations showed that without Planet 9, fewer TNOs come close to Neptune. Notably, without Planet 9, the number of TNOs that closely approach Neptune sharply decreases as distance from the Sun decreases, peaking only around 30 astronomical units. Conversely, with Planet 9, the close approaches happen more consistently over a wider range of distances, starting from about 16 astronomical units. To validate their findings, the team conducted a statistical analysis comparing the patterns observed in the simulations with actual space data. They considered observational biases and matched the simulation results with 17 known TNOs that have perihelia less than 30 AU and semi-major axes greater than 100 AU. The comparison strongly supported the model, including Planet 9, showing a much higher likelihood of 0.41 compared to just 0.0034 for the model without Planet 9. This substantial difference in probabilities indicates that the model with Planet 9 aligns more closely with the observed behaviors of TNOs, suggesting a significant role for Planet 9 in shaping their orbits. Later this decade, the Vera Rubin Observatory in Chile will start its operations, equipped with a powerful 8.4-meter telescope capable of conducting nightly all-sky surveys. This observatory will leverage the findings from recent studies, including those suggesting the existence of Planet 9, by closely observing the movements of distant TNOs. If these TNOs consistently exhibit patterns of proximity to the Sun beyond about 16 AU, as the Planet 9 model predicts, it could serve as a crucial indicator of the elusive planet's presence. This blend of cutting-edge technology and groundbreaking research can significantly deepen our understanding of the solar system's outer regions and potentially lead to the long-awaited confirmation of Planet 9. Recently, the James Webb Space Telescope measured how fast the universe is expanding. The results have confirmed the biggest crisis in cosmology, showing there's a fundamental flaw in our currently accepted model of the universe. If you learned new things from this video, please don't forget to like it and subscribe to our channel for more updates.